I've got a submission here. This user is running a ZMR 250 with DOI S1806 motors, GemFan 5040 props, and SN20A ESCs. So we might call this a little bit of a budget build. These are not top of the line components. There's nothing wrong with the components. There's no reason they can't fly well, but especially since one of the questions that you're asking about is yaw. We certainly could look to the components for some contribution to yaw-related performance. Yaw is the axis where quadcopters have the most trouble, flat quadcopters anyway, and the reason is that they use motor torque to generate yaw. And so the motors have to be able to spin up and, more importantly, spin down very quickly in order to yaw precisely. And they have to be able to spin up and down in a very controlled and precise manner, or the copter will become destabilized. And when you do a strong yaw move, the copter will have some coupling of pitch and roll. The number one thing, in my opinion, that contributes to good yaw performance is ESCs with very good braking. Another thing that contributes to good yaw performance is motors with a lot of torque, because torquey motors are able to spin the props up and down faster. Another thing that contributes to good yaw performance is smaller props and smaller motor-to-motor distance. And then finally, higher pitch props and props with more blades, tri-blades versus two blades, contribute to good yaw performance. And that's roughly in the order of importance from most to least, in my opinion. So if we're having yaw coupling problems on this copter, certainly we can try and tune it as best we can, but I think that if you're getting bounce back on yaw, then that may be a tuning issue. But if you're getting pitch or roll coupling with yaw, I think that's less likely to be a tuning issue and more likely to be an equipment issue. And we can see the SN20A ESCs, they're fine ESCs, but they're not like great ESCs. The 1806 motors, they're okay motors, but they don't have the most torque, right? So we're already sort of got the deck stacked against us a little bit. If we go to your config dump, we can see that you're running CleanFlight 1.11. And so the next thing that I want to check is, are you running the soft filters? So take a little side trip for a minute. The gyro chip that comes on the flight controller has a built-in low-pass filter on it to filter out high-frequency noise such as comes from the motors. And that's controlled by the gyro LPF setting. The default cutoff frequency is 42 Hertz, and that is very low. And the idea there is that you're going to heavily filter out the noise. You only really care about noise down below maybe 20 to 50 Hertz when it comes to flying the quadcopter. Everything else needs to go. So then what's wrong with this? And there is something wrong with it. The lower the cutoff frequency of this filter, the more latency there is. I think there's something like 8 milliseconds if my memory is correct. At a gyro LPF of 42, there's about 8 milliseconds of latency. And the less latency there is, the better the control loop, the PID loop, can do its job. Okay, so we would ideally like this number to be higher, but that would let more noise get into the system. And so CleanFlight 1.11 has these three settings: D-term cut hertz, P-term cut hertz, and gyro cut hertz. And they are software-based filters that Boris added to Betaflight some time ago. And so what you can do is you can set your gyro LPF to, I would suggest a value of 188 Hertz. I believe that's the correct syntax. I would suggest a value of 188 Hertz as a starting point. And you set your gyro cut hertz values. Oh, sorry. Set your cut hertz values. Say we set gyro cut hertz to something like 80, maybe. It's been a while since I tuned these soft filters. If you go to the right point in my YouTube feed, you can, or maybe you just search this thread, you can find a ton of videos of me talking about tuning these, but actually Betaflight has moved past these and now has a different kind of filter that is good enough that you don't need to tune it. It just works. And so it's been a long time since I tuned these, and I'm a little bit rusty on remembering what the numbers are. But if we set gyro cut hertz of maybe 60 to 80, I think is a good starting point, and gyro LPF to 188 hertz, what that will do is the hardware filter in the chip will be less aggressive and will have lower latency, and the software filter can do a better job than the hardware filter, keeping the latency relatively low. The other thing that is critical, if you don't do anything else, you must enable D-term cut hertz. The D term in the PID loop amplifies noise in the system. So if we look at your pitch axis and we look at the yellow trace, which is the D term trace, we can see that there is a lot here. This is even better. There's a lot of high frequency noise being expressed by that D term, and that high frequency noise is these sharp, narrow up and down spikes. That's a high frequency. If we just look at the gyros and compare them, do you see the gyros do not have a lot of spiky up and down motion? They do not have a lot of high frequency components. The D term has a ton of high frequency noise. And if we look at the yaw axis, wait for it, the yaw axis is just through the roof. Okay, so this will be significantly tamed by D-term cut hertz and will allow you to get your D terms into. Right now, the D terms are doing more harm than good in a lot of ways, especially on the yaw axis, because they're just so amplifying the noise. If we look at the motors, take a look at the motors as I play back. Do you see how the motors are just jumping up and down? Boris calls them angry Pac-Mans. That's making the motors run rough. It's making the handling of the copter worse, and it's just all around bad. So here's what I would suggest to start. And I haven't even gotten to looking at your actual tuning, right? We're not even there yet. We just got to get this thing a little more dialed in. So gyro LPF of 188 hertz, D-term cut hertz of, say, 18. That's a good starting point. It will probably significantly improve. And gyro cut hertz, by the way, even if you elect to leave gyro LPF of 42, still add this. But I also suggest gyro LPF of 188 and a gyro cut hertz of, say, 60 to 80, maybe 100. It just depends on how much vibration your copter has. A higher number will fly better, but will let more noise in. But let's say gyro cut of 50 and D-term cut of 17 and P-term cut of 50. But if you don't do anything else, D-term cut of 17 or 18 for sure. So then we could start thinking about what, these D-term traces should calm down. But the problem is that there's going to be significant latency on the D term, and the D term is going to be delayed relative to the P term. And they really need, the copter will fly the best when they are actually have the least amount of delay between them. That is not something you're going to be able to solve with CleanFlight 1.11. If you feel like flying better, I highly advise you to download Betaflight 216. Betaflight 216 will probably fly way better, and you won't need to adjust the filters at all because the filtering is all automatic, basically. There's a little bit of configuration, but you don't need to worry about this tuning and stuff. We put a whole lot of effort into learning how to tune these soft filters, and at the end of the day, Boris finally came up with a different kind of filter that works even better, and we just sidestepped the whole thing. Alrighty, so let's take a look at your actual PIDs. Here is your p-value on roll, or your p-trace on roll. And if we watch that playback, I'm just looking for oscillations. Here we can see it start to get a little oscillaty. Nothing bad though. In this roll, we can see it push into the move, and go negative, try to slow the move down. There's some activity here at the end. It's really hard. The thing is, it's really hard to judge some of these more extreme flight conditions. Notice, see, as you start to center your stick, it bounces back and forth. It's hard to judge these because the D term is so hyperactive, it's affecting the P term. I'm not sure how much I can say about the tune, given I'm out of practice tuning something from this far back. We're definitely seeing the P term start to get active during more extreme stick moves, but overall it's pretty docile. If anything, maybe roll P could come up a little bit, assuming you get your D term under control. Your rolls look sharp, they look pretty snappy, nothing to complain about there. So now we're going to take a look at some flips, front flips, and we'll take a look at your pitch axis. And again, I'm just going to get the D term out of there. Here we go. It looks pretty good to me. A little soft on the ending, maybe. Just a little soft, but pretty good. Nothing too much to complain about. Again, we can see times when the P term is starting to get active and is surging back and forth. No hard oscillations. I think your pitch and your roll P term are pretty close to correct for your setup. And now let's just check, because there's a bounce back at the end there, but I think your stick did it. Center the stick and then pulling back. It looks like you're getting some strong overshoot. Where's your gyro? Your gyro is the yellow one. Stick returns to center. Gyro stops. The gyro stops right as the stick returns to center and begins to bounce back. And we can see that bounce back, here is where the copter has stopped. The gyro has come to the line. And then the gyro crosses the line to negative, which means the copter is pitching back. And we can see the reason for that is that the I term is pulling it back. And that's now the I term and the P term are opposed. And then you move the stick, and then the P term gets in line too. So this is a common problem, and is a little. You might try reducing your I term on pitch, but I think the problem is better handled by increasing the P term if possible, which will give the P term more authority to cause the copter to do what it needs to do in the moment, and will reduce the I term's ability to cause the copter to do the wrong thing. Lastly, let's look for that yaw turn that you did. So here you're doing a yaw move, and I want you to notice that these mountains here, you're flying towards these mountains here as you start the move. Now the first thing I looked for, because you're talking about destabilization during the move, the first thing I looked for is, are you bumping the right stick? And you are not. So any destabilization is a result of a tuning or equipment issue. It comes back to center. It ends relatively abruptly after you come back to center. So there's a lot to like here. One reason that is it obvious that you over-rotated the move? Like you're rolled to the side because you rolled 90 degrees. You ended up yawing 90 degrees roughly. So that's why you're rolled to the side. You were pitched forward. When you roll 90 degrees to the right, when you yaw 90 degrees to the right, you'll be rolled to the left the same amount that you were pitched forward. That's just the way it works. So I'm not sure if it does look like the copter pitches forward a tiny bit as you enter the move. If we turn down the speed even more, just as you enter the move, it does look like it pitches forward a tiny bit. Maybe not. Right there. Right there, it does look like well, it's not pitch, it's roll at that point. It looks pretty good through here. Right there, it does look like it starts to lose it a little bit. Let's take a look at your motors and see if your motors are maxing out during this move. Yeah, see, here's the issue you're running into. Look right here. As you enter the move, these two motors can't go any slower, and these two motors are near the maximum. So what this tells us is that the copter is destabilizing because you're exceeding the authority of your system. It simply cannot yaw that fast. You need to reduce your yaw rate is basically what the answer is. These motors are at 0. These motors are near max. The copter can't yaw that fast without becoming destabilized. It lacks enough authority. The answer, well, it's tough to say what the answer is. The answer is probably a different setup. Motors with more torque, the props should be okay. 50-40 props. Your motor to motor distance isn't too bad. Honestly, the first thing I think people should do if they're having yaw tuning issues like this is get a set of great ESCs, like the Little Bs or the RG20s, or even KISS if you have a lot of money to spend. And the copter's handling overall will sharpen up immensely. But I would also suggest that you take a look at Betaflight 2.1.6, and if you are willing to step into those waters, Betaflight 2.1.6 is reasonably stable. I think it's as stable as CleanFlight 1.11, I dare say. It's a little bit of a different ecosystem and a little bit different stuff to learn about, but the defaults are very good, and the tuning is not that different. And there's all these other things like air mode and Acro Plus, and like, what is that? Forget all that stuff. If you just install Betaflight 2.1.6 and do your basic tuning, or even just try flying the defaults, don't even tune it, see how they fly, I think you may find that you get a much better flying copter, and that will make the most out of your system. But if you want one thing to do to improve your yaw, I think better ESCs will do it. That's just, there's nothing specifically wrong with your ESCs, but it's often the case that better ESCs improve yaw performance and make the copter handle better the rest of the time as well. The next thing I would say is go from 1806 motors to 2204 motors, and you probably get better performance. But I do the ESCs first, personally. But do Betaflight first, because it costs you nothing. It doesn't cost any money to try Betaflight 2.1.6, and I think you would like it. All right, that's what I got. Hope it's helpful, and happy flying.